Okay, hello everyone. What I want to share today is my own research. It is called Dynamic Holding Control to Avoid Bus Bunching, a multi-engine deep reinforcement learning framework. It is a research about a transition control with deep reinforcement learning method. And this research has been published in Public and Transportation Research Part C, and the link of this paper is below. So you can feel free to check this paper. Now let's begin our presentation. The presentation will be divided into 5 parts. The first is the background. So, what is the bus bunching? Intuitively, in public transport systems, bus bunching refers to the phenomenon where a group of two or more buses arrives at the same bus stop at the same time. And bus bunching has been a long-standing operational problem in public transport system. So, what causes bus bunching? Mainly there are two reasons. The first is the variability in travel time between stops. The buses may encounter different situations during the operation, so they may arrive at a bus stop with uncertainty. And the second one is the variability in passenger demands, which means that the passenger will arrive at the bus stop at random distribution, and the boarding and alighting procedure is also random. So both two variability will tend to cause bus bunching. And what is the result of bus bunching? For transit users, that it will have more waiting time and travel time, because once there are multiple buses arriving at the same stop, which means that at another stop there will be no bus, and the passengers there will have to wait. And naturally, for a transit system, such phenomenon will cause the uneven occupancy rate, so there will be a waste of public transit resource. So, in all, it will affect the level of service and undermine the reliability of transit system. And we will have a quick review on some related works to solve the bus bunching problem. There are multiple strategies to avoid bus bunching, since it has been a long-standing problem in public transportation operation. And as you can see, there are multiple strategies. For example, stops skipping, adjust cruising speed, boarding limit, bus substitution, and our today's topic, holding control. Among these strategies, the holding control is the most practical and adaptive one, because it will make passengers less frustrated, and it can provide better maneuverability to fit operation. So let's have a more detailed review on the holding control strategy. The holding strategies mainly have two categories. The first is the static control. The static control mainly means it is mainly twofold. The first is that the holding control is based on this fixed schedule, or based on a target headway. It has a very obvious disadvantages. The ideal achievable headway is neither static nor known in advance as a fixed value in reality. So if you implement holding control based on a schedule or based on a target headway, that it will hardly fit the reality. So the performance will tend to be bad. And the second one is the dynamic control. The dynamic control successfully solve the problem in static control. Usually the holding control can be based on a virtual schedule, or the holding control can be implemented through dynamic headway self-equalization. But it also has some drawbacks. These methods only focus on local control and tend to be lack of long-term consideration. So with this in mind, we want to develop a method to solve these two drawbacks. For the local control, the multi-engine consideration will be a good solution. For the lack of long-term consideration, the deep reinforcement learning is exactly uh, the one we can choose. So the multi-engine deep reinforcement learning is the solution to the holding control for bus bunching. That's what our research do today. And let's come to the methodology. First, let's have a problem statement. This is a representation of the bus corridor. Intuitively, there is a multiple stops located along the bus corridor, and there are fleet of buses to travel along the corridor to take the passengers at each bus stop. And let's have a more clear framework for the reinforcement learning method to implement holding control. As you can see here, the engines will be the buses and the environment will be the overall transit system. Let's have a more detailed look. From this picture, we can see what the formula, how we can formalize the problem into reinforcement learning architecture. As you can see, the engine is the bus here, and what he did is after he arrived at a bus stop, he can choose the action, and then the action means that and then the action will affect the environment, and then he will obtain a reward at his next arrival. So this will be a loop. At each at each arrival, he will determine an action, and the next arrival he will get his reward, and the reward will evaluate what he did, and this will guide him to improve his holding policy. Specifically, let's talk about each element of the reinforcement learning model. The first is the state. What bus engines should know when implement holding strategy? In our research, we just focus on 4 parts. The first three is local observable one. It includes forward highway, backward highway, and waiting passengers at corresponding stop. And the fourth one is what other engines are doing. This will be discussed later. It's also a very important element to guide the bus to implement a correct action. So what is the action? The action here is the interaction between bus engine and environment. Specifically, it is the holding period at corresponding stop. That's this in our paper. This is the action by bus J I at stop J, and this is a maximum holding period. So the multiplication of these two items will result in a holding period. That is what the engine will actually function in the system. And how do we evaluate this action? This is what the reward is introduced. This is why the reward is introduced. And according to the paper before, if we can reduce the mean and variance of the highway among buses, the bus bunching problem can be solved efficiently. With this in mind, we introduce subtrate reward function. The first part is to equalize the forward highway and backward highway. Sorry, there's a mistake here. And this part is used to introduced to the reduce the variance of the highway among each bus. And the second part is the holding penalty, which means that we should not hold a long period. So this can be used as to reduce the mean of the highway. Okay, now let's come to the solution to solve the reinforcement problem. And here is the multi-engine reinforcement learning framework. And maybe you already know this is a framework adapted from multi-engine reinforcement learning deterministic parser gradient, published in 2017, and I have made some modification and to let it fix with our problem. As you can see, there is an actor-critic framework, and the actor is parameterized the parsec function, which can use a deep neural network. The function of the actor is to produce an action based on its learned parsec, and we can implement action based on local observation here. The local observation is uh, as mentioned before, is the forward headway, backward headway, and the waiting passengers at current stopped. With this in mind, the actors can produce action. And the critic is the state value approximator. It is also a deep neural network. It is used to estimate the state value of the actor, and it is used it is used to help to update the parsec of actor. And the input of the critic includes the estimated actions and the local observation of and other and the local observation. And this is what other engines are doing. Introduced. There is where the what other engine. That's where the what other engines are doing stuff introduced. Because we because the actions of each engine is because if we do not know each what other engines are doing, the stationarity of the environment cannot be ensured. So we should have to we have to estimate the actions of each engine, and we use a joint action tracker to approximate actions based on global information to like the engine can predict actions of other engines. So we have estimated actions from other engines. In this way, we have imagined actions of others that can have a more detailed input. And we adopt optimize parameters for actors based on proximal parsec gradient published in 2017. And we can maximize the cumulative reward during each episode. And this is a natural problem of this is a natural optimization problem in parsec optimization. So we do not have a detailed introduction here. Another is the optimization of a critic. The goal of this part is to estimate the state value as accurate as possible, because the critic is used to estimate the state value of the actor. If the estimation is not accurate enough, the update of the actor will not be accurate enough. And this deep Q-learning based method. So yeah, so this also very straightforward. And the third part is the optimization of joint action tracker, because we have to approximate what other engines are doing at each arrival. So there is a there can be a supervised learning problem. And this is the overall optimization procedure. Maybe you can check this procedure in the paper, and we will not have a detailed introduction here. Now let's come to the simulation study to demonstrate the performance of this method. Now let's begin with the setting. Actually, there is 12 uniformly distributed stops in a ring corridor, and the boarding time is the 3 seconds per passenger, while the arriving time is 1.8 seconds per passenger. There are 6 buses evenly distributed every 2 stops, and then they begin to run and service each stop. They maintain a constant speed at 20 km per hour, and the max holding time is set as 180 seconds. And we set a Poisson distribution for the passenger arrival dynamics. And what we and we implement this statics with a simulator written by Python and the learning model uh, based on TensorFlow. This is the interaction between the simulator and learning module. And we compare our method with the following 5 baselines. The first is the no holding control, which means that we do not implement a specific control strategy, just let the bus running on the corridor by its own. And the second is the naive harding control, and, where we will introduce a target heavy. And the naive schedule-based holding control, we will introduce a target schedule. And there are also some dynamic holding control strategies which consider backward headway or forward headway. And we will introduce 3 evaluation and index. The first is the average holding period, because we should ensure that we can solve the bus bunching with as less as possible holding period. In this way, we will have less frustration of passengers. And the second is the average waiting time per passenger and the occupation dispersion at each stop, which is passenger oriented and transit system oriented goal. And first, we can have the training procedure of this framework. As you can see, this is the training procedure of actors. This is the total reward. This is the 2 parts of the reward. The first is the reward for holding penalty, and this is the reward for habit equalization. And as you can see, the convergence is promised. And the second is the training procedure for the click network and the training procedure for the joint action tracker. Now let's see the model comparison. And if we do not implement any holding control, the bus bunching will happen, and it just looks like this. As you can see, multiple buses are arriving at the same stop, so the trajectories of them are overlap. This will cause low efficiency and will result in a much longer waiting time for the passengers. And when we implement different holding strategies, we can see that the trajectory has a different look. So if hard holding control or the schedule-based control, we can see that the trajectory is more the heavy among the each buses are more equalized, and the backward heavy control policy and the forward heavy control policy also will improve the bus bunching phenomenon. And let's see our method. Specifically, we can solve the bus bunching problem. As you can see, the head weight among each trajectories are equalized, and what's more important is that the black dot means the holding control, means the location of holding control, and the more black the dot is, the more holding period there is. As you can see, the proposed method implement a shorter holding control while succeed in avoiding the bus bunching scenario. And let's look at the comparison in different index. The first is the bus rows at different stops under different strategies. As you can see, if the bus bunching happens, the bus rows of at different stop tend to be a large gap because there is one bus that take all the passengers, while other buses arrives at the bus stop. There is no passengers because they just arrive because the bus bunching happens. And if we can avoid bus bunching, the load of each bus tend to be equal and the resource will not be wasted. And the second is the holding period and waiting time occupation dispersion. As you can see, our method also presents a very smooth and better performance compared to other methods. And let's look at stopwise. At each stop, we can see a similar better performance of the proposed method. Now let's come to the conclusion. The contribution of this research is that we establish a multi-engine deep reinforcement framework to implement dynamic holding control with proper design reinforcement elements. In this method, we introduce joint action tracker to approximate actions of each engine and design a learning procedure based on PPO to train engine efficiently. And in the end, we develop a real-world transit simulator and implement multiple quantitative analytics to demonstrate the superior performance of the proposed model. And there are still some limitations of this research. More uncertainties in fleet operations become considered because in this research we just fix the cruise speed of each bus, and the arrival rate of the passenger is also fixed. In addition, we did not consider the traffic signal in the operation. And also, more available information can be incorporated in the future, just like, for example, the real-time passenger demand. If we can have more available information, we can make a more clever policy. And in the end, we hope to test the framework in the real-world fleet operation. That's all. That's my selected reference, and thank you.